and welcome to this video on the road to quantum reality. We have come quite a way on our journey by showing the presence of stable structures having spin and the same form as solutions of the Schrodinger equation. But these structures have only been shown to exist in a stationary ether. They must, of course, be able to exist in any state of motion relative to the ether. Otherwise, the whole exercise is a waste of time. In the last video, we took a bit of a detour to show how de Broglie's original work was based on the postulate of the harmony of the phases for motion obeying the rules of special relativity. Notice that de Broglie took special relativity as a given. He didn't show that special relativity could be explained as a consequence of his findings, but he came the other way. If nature requires special relativity, then P equals h bar k. We are not in this position. If real wave quantum mechanics has some fundamental validity, then we would really like to show that it leads to special relativity, rather than just accords with it. That seems to be a big ask, but on we go. Recall this animation of de Broglie's matter wave. He had a wave and a particle, and the aspect of the particle which he surmised was an oscillation, just some real number changing in a sinusoidal manner at a point in space where the particle was, like the blue line in this animation. Through the principles of phase harmony and special relativity, he showed that this oscillation must slow as the particle velocity increases in the manner of a clock, and that it remained in phase harmony with a superluminal matter wave whose frequency increased with particle velocity. Putting these things together, he showed that the matter wave must obey P equals h bar k, and also that the product of the particle velocity and the wave velocity was c squared. Schrodinger used this P equals h bar k relationship as input to his plausibility derivation of the Schrodinger equation, and the rest is history. We know that our structures are quite complex, containing phase patterns which we are yet to understand, and modified wavelengths as the result of their varying energy level. But to keep things simple, we can start by looking at a row of FRs exactly one wavelength apart, each having the same phase and existing in a stationary ether. A word of warning: we are going to get the wrong answer doing this, but in the process we will see some things much more clearly, so it is well worth doing. Don't read too much into this animation. I could have drawn it as a line going up and down, or equally a rotating arrow. I'm just trying to indicate the phase of the FR and their spacing. What we are really interested in is the backward and forward waves emitted by the FRs. The restriction to backwards and forwards arises because we are looking at one dimension only. Recall that we showed that the expression for forward and backward waves was as shown here. When the x and t terms have opposite sign, the wave is to the right, while if they have the same sign, the wave is going left. Changing both signs does not affect the direction, but it does shift the phase by pi radians. Now, once again, we put the FRs at the integer positions along the line. This means that the value of k must be 2 pi, because we need 2 pi radians of phase per unit distance. As always, we assume that the speed of light is 1, so since in general omega equals ck, this means that the frequency must also be 2 pi. As a check, lambda equals 2 pi over k, so this means that the wavelength is 1, which is what we want. We also want the phases of the forward and backward waves passing through each FR to differ by pi radians. Remember that we are applying discriminators which relate phase and wave direction. Here the directions are opposite, so the phases must differ by pi. This requires that the FRs are nodes of the standing wave resulting from the forward and backward waves. So we want the node of the standing waves formed by the backward and forward waves to be at the integer positions. We can ensure that this is so by using the two waveforms shown in this animation. You can see that the origin is a node and remains so when we set the animation going. What would happen if this row of FRs was moving to the right through the medium? Well, waves going to the right will be Doppler shifted to a higher frequency, while those going to the left will be Doppler shifted to a lower frequency, in line with these two standard equations. Now there will be a moving standing wave, and we can deduce from our own phase harmony principle that each node must be the location of an FR. In this animation, we allow for one FR, and hence for all of them, to move at the velocity v to the right. When v equals 0, we have the same animation as the last one. But look what happens when we let the FRs have a very low velocity of, say, 0.01. We seem to have essentially the same standing wave modified by a rapidly right-moving phase wave. If we increase the velocity to 0.1, the phase wave has a shorter wavelength and is moving more slowly. If you look carefully at the location of the nodes on the x-axis, you can see them travelling to the right. It is all very well to say that the wave is shorter and is moving more slowly, but we would really like to quantify this effect. Actually, this turns out to be possible. We get this equation where the two factors are a cosine and a sine function. We won't do the maths here, it's a bit tedious and will break our flow, but we can at least show that it is the case in this animation, where we plot the function found as the sum of the forward and backward waves alongside the product function for some different FR velocities. They are exactly the same because they are indeed mathematically equivalent. What can we say about these wave factors? Well, the first wave, k value, is dependent on the difference between the two omegas. For low velocities, this difference is very small, so the first wave is not very wavy in space at low velocities. But its frequency is the average of the forward and backward frequencies, so is very close to omega naught at low velocities. The second wave has k as the average of the two frequencies, so at low velocities it looks very like the original standing wave, except that its frequency is in the difference form and is very small. It is barely going up and down at all. It looks as though it's almost frozen in space. Now, the real wave is the product of these two waves. So, at very low velocities, we take an almost stationary standing wave and we multiply it by a phase wave of approximately average frequency to get the correct result. For this reason, we can say that the real wave has been factorized into the product of a phase wave and a standing wave. But what is the k value of the phase wave expressed in terms of FR velocity rather than the resulting Doppler shifted frequencies? Well, we just substitute for the Doppler frequencies and solve. First, we set them on a common denominator in the green expression, using the fact that 1 minus v upon c times 1 plus v upon c is 1 minus v squared upon c squared. Then we open out the brackets, and then the omega naughts can be cancelled out. Now I use the standard SR abbreviation in red by letting gamma equal 1 upon the square root of 1 minus v squared upon c squared. I know I used the non-inverted form in an earlier video because it was convenient, but because we are going to be comparing results with SR quite a lot, I will adopt the normal form from now. Anyway, when we make the substitution, we get the green equation. We notice that when V is non-relativistic, gamma squared is very small. And since omega naught and C are constant, this equation says that K is proportional to V. Obviously, we don't have the correct constant of proportionality yet. We would need a mass term so that we could get to P equals HK. But we can see how the phase wave is intimately related to matter waves, and hence the Schrodinger wave function, at least at non-relativistic velocities. It is beginning to become clear that a lot of the problems in interpreting Schrodinger waves is because they are just one factor of a real wave. The standing wave has been lost in quantum mechanics, although we will later see that it keeps trying to show itself in the form of interpretational issues. While we are at it, we can do similar substitutions to express features of the factorized waves in terms of V. Apart from the green one, which we just found, we find that the distance between the FR nodes reduces as gamma increases, as shown in the blue box. This is beginning to sound a bit like length contraction, although with the wrong factor. And the product of the FR velocity and the phase velocity of the P wave is c squared, which is also familiar. It is the same result which de Broglie found. So, in terms of takeaways, it looks like the Schrodinger wave is just one factor of a real wave, and you can only start to attribute some physical reality to it by including the standing wave factor. Also, we are beginning to see some echoes of special relativistic behaviour, but we are not there yet. Our examination of linear oscillators has precluded any consideration of spin, and it has also precluded any consideration of phase harmony with FRs not in the direction of motion. And we have the wrong factor for special relativity, namely gamma squared rather than gamma. And finally, we are missing any concept of the mass, which is essential in considering special relativity. But we are getting there, and in the next video we will show how extending to 2 or 3 dimensions will take us the remaining steps. Thank you for watching this video. I really hope you are enjoying the journey along this road as much as I did. So please like and subscribe and tell all your physicist friends.